The reason you're watching this video right now is because an algorithm recommended it to you. If you look at the YouTube homepage, you will see a few dozen videos that were selected specifically to you from literally billions of videos. Until today, viewers and creators on YouTube treated this algorithm as a mystery, a black box that we will never fully understand. But I've found something. In 2016, YouTube quietly released a new paper titled Deep Neural Networks for YouTube Recommendations. This paper showed with unprecedented detail how the YouTube algorithm actually works. Since this paper was released, almost nobody on the platform even talked about it. What if I told you we can trace back the advancements in AI starting with this 2016 paper and make a very good guess about how does the algorithm works today? While we can't be 100% sure, Google left a very interesting trail of technical clues. And this video is about following that trail and seeing how far will that trail take us in the rabbit hole of the YouTube algorithm. 2016 was the point that YouTube moved from only looking at performance like clicks and likes to personalizing videos to every user. So the paper that they published that explains how they do it will be our starting point. We'll first try to understand the entire paper, and it's a complex deep dive into multiple deep learning models. We'll try to understand why did they choose to use this specific architecture, what are the limitations that made them use it, and the advantages of this architecture, and what has changed since. We'll go over specific advancements in machine learning that happened since this paper that could directly improve the architecture they described there. Now, this video is the most complex video I've ever made, so it's going to take a pretty long attention span to really understand what I'm talking about. But if you give me your patience, I promise that by the end of this video, you will see the most accurate and insightful blueprint of the YouTube algorithm ever presented to the public. So without further ado, here is the 2016 paper. So I think one of the easiest starting points for this paper is the flowchart on the second page. It shows that the YouTube algorithm is separated into two parts. The first part is the candidate generation, and the second one is the actual ranking. Now, I found it extremely difficult to just go over the paper, go over the flowcharts, all of the text, and try to understand how all of those different systems fit together. So I created this high-level diagram that shows how did the YouTube algorithm worked in 2016. Now let's do a small deep dive into each one of those parts. First of all, we can notice something very basic that we know would not change ever. The purpose of the algorithm is to take a user and all of the videos on the platform and find the best videos to show that user to maximize some parameters that align with the interest of YouTube. Now, let's put ourselves in the shoes of YouTube. We have a lot of data from previous people watching videos on our platform, and we have a lot of good engineers. So, let's say we just create a model that takes a video and a user and predicts how much time would the user spend watching this video, what's the percentage of him liking the video, and how much is he likely to be satisfied and stay on YouTube after watching that video. Then we can just sort the videos based on how it predicts the user would interact with each video and show them the sorted list. Well, actually this would be a horrible solution, because we would need to run this model on every single one of the billion of videos that we have on our platform every single time the user views the homepage, which is simply infeasible. It would never be feasible. So this two-stage system that was described on page 2 is specifically designed to combat that and to approximate an algorithm running on every single video without needing to actually run it on every single video. The way YouTube achieved that is by first encoding both the user and the videos into an embedding space. You can think of it as having a huge grid of all videos, but the position of the videos on that grid is correlated to the content of that video. We will refer to each point on that grid as a video embedding. And the only catch is that here it's a two-dimensional grid, so each video is associated with two numbers, but in the real algorithm, each video is associated with much more numbers. The space is very high dimensional. So you can think of video embedding either as putting the video on a space where similar videos are closer together, or generating for each video a list of numbers, and videos that are similar to each other have similar numbers. Both are equivalent. Now there is a slight catch here. Converting a video into an embedding that represents everything we need to know to understand which user, which viewer is interested in that video is a very non-trivial task. And back in 2016, with the scale of YouTube, it wasn't just non-trivial, it was impossible. So now let's focus on a simpler task. How do we encode a user into an embedding space? You can see that I colored the user encoder module in purple. That means that it is a deep learning model. And the paper actually shows us exactly how did they build that model. Let's focus on the bottom part of the diagram. Those blocks represent the input of our model. The first block is embedded video watches, which is exactly the part that we said is extremely non-trivial to get. So let's ignore it for now. The next block is embedded search tokens, which is just embeddings of the text that the user searched before. The next part is a wide list of features that represent each user, like geographic location, age, gender, and a wide range of other ways Google respects our privacy. Another interesting thing you might note is that the video history and the search history are both averaged before we input them into the model, which means we don't put in every video we watched, we actually average all of the last videos we watched, all of their embeddings, before inputting them into the model. Then we're going to take all of those inputs and pass them through a feed-forward network, and project those inputs into a 250-dimensional embedding. This is what we call the user embedding. But if everything I said right now doesn't really make sense, you are actually correct. It doesn't. Because I said that it's pretty much infeasible to get with a deep learning model the embedding of a video, and then I said, okay, let's ignore it for now and get the embedding of a user. But then a user embedding is dependent on the embeddings of the videos that he watched. So actually I didn't make anything simpler. Kinda. The truth is that they are dependent on each other, as symbolized by this little line. At the start of every new video, the embedding of that video is starting as just a list of random numbers. But every time a user watches that video, it pulls those random numbers a little bit closer to the user embedding. So similar audiences attract similar videos. But if you remember correctly, also our user embedding is depending on the video embeddings. We actually average out all of the videos that we watched to get something for the user embedding. The way you can think about it is that every time a user watches a video, it attracts this video a little closer to the position of the user embedding. But also, this user embedding is updating to accommodate for both the video that he watched right now and the videos that he watched before, kind of moving the user embedding a little closer to the average of all of the videos that he watched recently. It's a bit like there is some sort of gravity between similar audiences and similar videos, with a little bit of grounding that comes from the extra information that we put into the user encoder, like what did the user search, his age, geographic location, and some personal details. So the first part of the YouTube algorithm is designed so we can put both users and videos onto a space where in that space similar audiences and similar videos are closer together. And that would make it much easier to understand the next part, the top case similarity. This top case similarity process is very simple. It just means mapping our user onto that space using the user encoder, and then just find the X closest videos to our user. Those videos are our candidates for being recommended, and this summarizes the candidate generation part of the paper. the candidate generation is exactly everything we talked about so far. So this whole process is designed for us to have a very fast way to take millions or billions of videos and find a few hundred videos that are good candidates that we can invest more computational power using a bigger model and see which of them we want to recommend to our user. Well, now there is only one part in the paper left for us to understand: the ranking model. Luckily, this one is pretty simple. Remember our naive model from the start of the video, where we just take a video and the user and predict what's gonna happen if we show that video to that user? And we said that we can't use it because there are too many videos on YouTube. Well, this is exactly this fine ranking model. Because after we extracted the most likely candidates, we can invest in a much heavier model because it's just going to run on a few hundred videos and not billions. You can see that I also colored the fine ranking model in purple because it's also a deep learning model. And you guessed it, the paper shows exactly how this model is built. Now, this flowchart feels almost intentionally confusing, so let's dissect it part by part. Like in the user embedding model, those little boxes represent the inputs of our model. And like you can see, the fine ranking model input is made of both user things and video things. This is the part where we have one model that combines features from both our user and our video. So the first part here is the impression video ID that goes into the video embedding box. This is just a very confusing way to say we input the embedding of the video. You know, the position in the space that represents what this video is about and what audience like the video. The next input, where it says watched video IDs, that goes into the video embedding and then the average. This is just the average embedding of the last n videos we watched, the last 50 or something videos we watched. The next input is both the user language and the video language, and the language is encoded into just a list of random numbers that represent English, a list of random numbers that represent Russian, Spanish, and any other language, and just to give the model a little bit more context about both the video and the user. The next one is actually very interesting. I thought time since last watch is time since the last time the user watched this video. But actually YouTube did something much more interesting. They count the time that passed since the last time the user viewed a video similar to this video. Not exactly this one, as some types of content are good for binge watching and other types are good for like viewing once every week or even once every month. And we want this model to be able to learn those patterns. The way we know how much time passed since the last time the user viewed a similar videos is by checking the distance in the embedding space of all videos. And we check the last time the viewer have viewed a video that is within a particular distance from the video we're considering to suggest to him now. And the last parameter, which is previous impressions, is just a measure of how many times did we show the user this video and he didn't click on it. All of those inputs are fed into a feed-forward network, and we train this network to predict one thing and one thing only based on those inputs. How much time would the user watch the video? Now, let me clarify one thing about this watch time. This is not the amount of time the user would watch if he would click on that video. That's the average time the user would watch the video if we show this user the thumbnail of this video. So it includes also the click-through rate. So if the model predicts that the user would not actually click on that video, the estimated watch time would be close to 0. I've actually also redesigned a simplified version of that flowchart that is much easier to understand. You can see that we have the same inputs, network, and output, just in a more simplified way. And please remember that flowchart for later, as we are going to build on top of that. So let's do a small recap. So the whole paper starts by having all of the videos and our user. We pass both of them into a system that creates an embedding for each user and each video. And those embeddings represent what are the videos about, or what does this user usually watches. We use top case similarity to find the closest videos to our user in our embedding space, to filter out billions of videos and get just a few hundreds of good candidates. Those candidates are passed into a deep learning model, the fine ranking model, to create our actual recommendations. Now note that this fine ranking model is only scoring the videos based on one parameter, watch time per impression. There is no likes, no comments, no engagement, nothing like that. It's just watch time, at least in 2016. Okay, I know that's a lot to take in, but that's pretty much the whole YouTube algorithm, at least in 2016. Now, while a lot changed since, a lot of things actually didn't, and I believe a lot of the structure remained very similar until today. One thing that is probably extremely similar is the importance of the impression to watch time ratio. So creators creating videos have two ways to increase the impression to watch time ratio. One way is to make viewers watch the video longer. And the second way, it's actually much easier, is just making more people click on it. And typically the lowest hanging fruit and the best way to get more views is getting more people to click. So designing better thumbnails is probably the most important part in making more successful videos. And that's why I want to introduce to you guys to the sponsor of this video, Kittl. Kittl is an AI-enhanced design platform that makes you a better, faster designer. Kittl is a tool for making professional designs, from print to merch to amazing thumbnails, in one unified workspace. With no download needed and an extremely fast learning curve, you'll be able to get professional results even as a beginner. And the AI tools within Kittl are not designed to take away from your creativity. They are set up in a way that actually encourages your creativity and keeps you in control, while also removing the friction that comes with designing anything. Okay, I want to show you a really cool feature I found here. It's called Smartboards, and let's start by this example, because this is just a YouTube thumbnail that I designed. And I create a new smartboard and describe to the AI what changes I want to make to this version. So let's try to add a small outline. Now I don't really like this direction, so we can go back to the old one and then create a new smartboard and try a 3D direction. And then we can always choose if we want to continue explore each one of those paths or go back and try something else. And on the way creating an evolution tree of our designs. Now honestly, I didn't know about Kittl before this sponsorship, but after learning about them, I'm seriously considering myself moving all of my design work to there. So I would really personally recommend them and encourage you guys to check them out. You can try using Kittl for free right now. And if you want to just try them out, now is literally the best time, as all of the hottest AI models will now be free. And for you to take advantage of this partnership, please use the code GALLAHAT when you check out to any plan and you will get 25% off. Now let's get back to the video. Now that we know how the algorithm worked in 2016, we can get to the more interesting part of the video, which is how does it work today. And while today the algorithm should be a secret, I think you'll be surprised by just how much we can say about how it works today. One thing that we know is very different from 2016 to today is that today we have a lot more compute, we have a lot more GPUs. So even if we keep the architecture completely the same, there are two things that we know would change just by the fact that we have more compute. The first one is that instead of just a few hundreds of videos as candidate that goes to the heavier model, we will have maybe thousands. We can go through more candidates. And the second thing is that the video and user embeddings are just 256 dimensions in 2016. With more compute we can handle larger embedding spaces, probably with a few thousands of dimensions as well, or maybe even tens of thousands. But of course, since 2016, things improved massively in the AI space. Just 9 months after the YouTube recommendation paper was released, a new paper was released into the AI world, a paper that would become one of the most influential papers probably ever released. It was also released by Google, and you probably heard it as the "Attention is all you need" paper. This paper would become the foundation for the transformer model that would then power all modern LLMs like ChatGPT, Claude, Gemini, and pretty much all other models. But it's not only useful for LLMs, and the use case for the YouTube recommendation screams the need of attention mechanisms. Attention mechanism allows us to understand relationships between parts of our data. And I have another video about attention if you want to see it. I'll put a link in the description. Now, if we allow ourselves to use attention, we can massively improve this architecture. The first thing we can solve is the cold start problem. That when we upload a new video, the algorithm actually doesn't know what the video is about. It needs to get a lot of views to do the attraction of audiences and similar videos mechanism that we described earlier. The way we can help the system understand what the video is about instantly using attention mechanisms is by building a video encoder. Those are models that can produce video embeddings just by the content of the video itself. It doesn't need YouTube, viewers, or any other models to determine that. Just input a video and we get X-dimensional representation of what the video is about. This was impossible before the Attention is all you need paper, as understanding a video and the language within it requires us to have an understanding of the data that is currently only possible with attention. So this would allow us not to just create random embeddings for a new video being uploaded, but actually know a very good estimate of where we should put it within the embedding space. It's likely not a replacement of the old system, but an addition to it. So probably the old mechanism of users attracting videos and videos attracting users is still at least partially in place. The next thing attention can improve in this model is allow us to expand the input parameters. In the original 2016 paper, they actually stated that a great care was taken to withhold information from the model. That means that they intentionally didn't give a lot of parameters to the model, and they could have given it more. But if we introduce attention to the model, we don't need to withdraw information from the model and carefully select just what is directly relevant, as attention mechanism is very good at needle at a haystack problems. So even if we have a massive amount of input data and only small amounts of it is relevant to the decision making, those models would be able to identify the relevant parts. And that would allow us to go from just fewer than 10 signals per model to, in 2021, YouTube released an article where they stated they use more than 80 million signals. And that's also an improvement that is directly correlated to the attention mechanism. So the attention mechanism and the extra compute allowed us to create also a video encoder and not just a user encoder. And this video encoder is both useful for solving cold starts, as now we can immediately infer some attributes about the content of the video, but also it allows us to do something that seems almost magical. Anytime we have two encoders of vastly different kinds of data that are related to each other, like users and videos, we can use a machine learning training technique called Contrastive Learning. One cool example of Contrastive Learning is OpenAI Clip model that allowed us to connect images to text. The way Clip works is by having two encoders, one for text and one for images. Those encoders encode both the text and the images into, let's say, 1,000-dimensional space. Now, let's say we want to organize this embedding space, so images would be close to the text description of them. So an image of a cat on a tree would be close to the text, a cat on a tree. we can train the two encoders to produce the answer of the other encoder. So when we pass an image of a cat on a tree to the image encoder, the loss would be the distance between the embedding that this image encoder produced and the embedding that the text encoder produced for the text, a cat on a tree. So in simpler words, those two encoders create an embedding space where images are close to the description of that image and far from every other piece of text. So like a cat on a tree would be very far from a description of an AC remote. But this technique is not limited to the connection between text and images. We can use the exact technique to map the relationship between videos and audiences. So the addition of the video encoder does not only solve the problem of a cold start in terms of not understanding the content of the video, but also the video encoder can now understand the relationship between the content of the video and the audience before even a single person watched that video. So while they never publicly admitted of using the contrastive learning technique, it's pretty obvious that they would, because the benefits it would bring this architecture are immense, and the engineers in YouTube, they know those techniques. So we implemented attention, we increased the embedding size, and we introduced contrastive learning. But all of those things, while extremely effective, are only things that affect the candidate generation, and not the actual ranking model. So let's try to figure out how did the ranking model itself changed since 2016. So you might think again I will just go back into adding attention layers and making the model bigger, to try to think what changed since 2016. And while those things are likely true, we can actually get a lot more detail about what changed in the ranking model since then. In 2019, YouTube actually released a new paper. This new paper is about recommending what to watch next, or you might know it as the recommended videos on YouTube. Well, this paper is actually a lot more complicated than the paper they released in 2016, so I'm not going to deep dive into every single part. But there are a few things that we can learn from how they implemented this new system that can make our speculation a lot more accurate about how did the original system evolved and the homepage recommendations. One thing that they changed is that the ranking model is not only producing watch time prediction now, and actually predicts a lot more parameters. And while the ranking model in the 2019 paper is not the same ranking model as the one in the 2016 paper, as one of them is used to recommend videos on the homepage and another one is about watch next, we can be pretty confident that if they found value in not only predicting watch time in the watch next, they would also want to not only predict watch time in the homepage, but actually get more signals that might indicate the satisfaction of the user. So while it is a little bit of speculation, I think we can be pretty confident that a lot of the innovation that they introduced into the watch next ranking system, it's also things that they introduced into the homepage ranking system. So let's see how they did it. So you probably remember the ranking model that we talked about that appeared in the 2016 paper. The one that we use to score videos based on watch time. In the 2019 paper for the watch next recommendations, they actually introduced a new kind of ranking model. And this new architecture and new model is a direct improvement of the old one that they described in the 2016 paper, and can be very easily compatible. So I want to walk through what I think they updated since 2016 based on the 2019 paper. Of course, we are starting with the signals. Many of them are the same, but for the newer one we have a lot more. As we said earlier, because we have attention, we can introduce far larger amount of parameters without confusing the model. The feed-forward part is replaced by a mixture of experts model. This is an efficiency technique in machine learning that allows only some parts of the model to be active on every inference. on every time we use the model. This mixture of experts is not used to predict a single value, like watch time, likes, or so on, but it feeds into many what they call gates. They have a watch time gate, a like gate, a comment gate, a share gate, and every gate is used to predict a certain user behavior. Note that this model is built from many different models. We have the main mixture of expert model, and this model feeds into many gates, and every gate is also a machine learning model that is trained to produce the particular results. Those results are then weighted based on the business interests of YouTube and combined together to form the overall video score. So we can sort all of our candidates based on that score and get our recommendations. So let's just do a small recap about how do I suspect the YouTube algorithm works today. Similar to before, we start with a user and all of the videos on the platform. A user is being fed into a user encoder to produce the user embedding, and every video has already passed through a video encoder to produce a video encoder. Those two encoders are contrastively trained, which means they are trained to produce the result of the other. On top of that, I do believe the old system is still here, so the video embeddings, or at least part of them, are still dynamically changed the more views it gets. So viewers are also updating the video embedding to describe better and better what audience like this video. When we want to generate the candidates for being recommended, we use top case similarity between our user embedding and the embeddings of all videos to find the closest ones. Those candidates, together with our user, are fed into the fine ranking model, which is now a mixture of expert model that feeds into many gates, each gate supposed to predict a certain user behavior. Those user behaviors are weighted and combined to produce a video score based on the interests of YouTube. And those scores are how we sort our candidates, and the ones on top will be recommended sooner. I think now it's a good time to tell you that if I made any mistakes or any wrong assumptions, I would like you to tell me in the comments and I'll correct myself in the description. Anyway, now the question is, did we finish? Is this how likely the YouTube algorithm is today? So actually I've found a few more things that tells me that no, this is not the full story, and there are a few more systems that we're missing. YouTube publicly acknowledged many times that they are actively demoting videos that contain misinformation or conspiracy theories. I believe the way they do it is by using a second penalty model that is connected to the video encoder. The job of this model is to identify patterns in videos that goes against YouTube guidelines and business objectives, like conspiracy theories, misinformation, and I really hope they didn't program it to prevent the exposure of the YouTube algorithm. The next problem is relying on top case similarity for the candidate generation, as if we always choose the best candidates, we actually would keep the user in a bubble of everything they already watched, and the user wouldn't be able to really discover new things he likes on YouTube. That's actually a very common problem in machine learning that appears in a lot of systems beyond the YouTube algorithm, and we have a lot of ways to combat that. I think they do here in the YouTube algorithm something similar to what we do with large language models, where we have a temperature with the top case similarity that adds a bit of randomness and allows us to choose not the best candidates, but have a fuzzy edge around it. Now there is actually one more thing. You know that LLMs have gotten into pretty much every modern system now, but it seems like they wouldn't really help the YouTube algorithm. No, of course they would, I'm really just kidding. Currently, Google is the only company in the world that managed to make a model that natively can understand video. I'm talking about the Gemini models. Now, without getting into the details, they had to produce some sort of video encoder to be able to encode the video into tokens that the model can understand. And this video encoder was trained in parallel with the main LLM. And because LLMs have such a rich understanding, this video encoder would become pretty much the best at understanding video. So I was thinking, what if part of the 80 billion signals that they use to analyze videos are the embeddings produced by Gemini video encoder? Now, I know that sounds really speculative, more than anything we said so far. I'm just connecting different things that Google did. But I've found something. We can actually do an experiment by uploading a video file into Google Drive, let it encode so we'll have a player similar to YouTube, and uploading a video to YouTube. We can use both Drive and YouTube to input videos into Gemini. And when we do it, it loads the video to produce the tokens that go into the model. Now, I wanted to measure the time it takes to produce the tokens for the same video from Google Drive and from YouTube, because I suspect the embeddings from YouTube already exist. The video probably already went through the model and they probably saved it. And this is the results. For uploading a video from Google Drive, for the same video it took 6 minutes. And if we use a video that was already uploaded to YouTube, it doesn't matter if the video has 0 views, it would take less than a second. Now, I don't know about you, but there is absolutely no way such a complex encoder would encode a full 4K 60 video within a second. There is no way. It has to be the case that they already encoded the video with this model before and cached the results. And that's the reason I would assume that part of the video encoder is Gemini. Now, if anybody from YouTube watches this video, please, I know you can't, but secretly just comment below how close did I get. Am I accurate or am I way off? As there is a very real possibility that I'm just completely wrong about most of it. And I want to finish off the video by talking about politics. I see a lot of things that are going on in the world, and I want to ask my community for one thing regarding that. I don't know if you are left politics or right politics, but any group that you identify with, don't let yourself agree with all of their values. Find at least one value that you agree that goes against your group. Because if you find yourself agreeing with everything within your political group, it means that you never independently think about those issues. So for the sake of the world and making people a little less extreme, let's find at least one thing that we don't agree on with the obvious political group that we are affiliated in. I really hope you enjoyed this video, and I'll see you in the next one. Bye bye.